There's 3 different types of glassware that can be used. So conical vials, those usually are used to hold volumes that are less than 4 mils. We can use centrifuge tubes. We typically use the screw cap centrifuge tube, and that's for volumes of 4 to 10. And then we have something called separatory funnels, or sometimes it's called SEP funnels. And those are usually for bigger volumes, greater than 10 mils, and they make really large ones for doing extractions, and they make smaller ones too. So it turns out, and we talked about this a little bit up above, but it turns out that when 2 immiscible solvents are mixed, for example, in our example above, we had diethyl ether in an aqueous layer. The solute, right, that in our example up above was naphthalene, right, and benzoic acid. They distribute themselves between those 2 liquid phases because there's some solubility of benzoic acid in the ether and a little bit less so of the naphthalene in the water. Okay. Now, when you do this, so here, if you look at this first little conical vial, here you have ether, and now you've added water. So here's your aqueous layer, for example. Here's your ether layer. We call the top ether layer, sometimes we call that the organic layer because it's the organic solvent. And if you look at this, I know it's kind of hard to tell, but you have black dots and you have these kind of open circles. And when you add 2 different solvents, you end up having some black dots. This black dot is actually up here a little bit. And then down here we have our open one, right? So there's a little bit of the black dots coming up in the top ether layer, and also a little bit of these round circle guys coming down here below, right? So we can measure that. That's an equilibrium kind of constant that can be calculated. And it's calculated the following way. But that distribution coefficient, again, it's an equilibrium constant. Numerically, it's equal to the molarity of the solute in the top layer. That's T, stands for top, divided by the molarity of the solute in the bottom layer. And it's pretty straightforward to calculate. So if you're setting this up, what you would do, right, from molarity, it's the solute mass divided by the molar mass. That's the moles divided by volume. That's molarity. Okay, it's molarity top. And then down here, that's molarity at the bottom. So what we try to do when we carry these things out, just to make life a little bit easier, is that so we're talking about the same compound. So it'd be the K value for naphthalene in ether and water. All right, the K value for benzoic acid and ether and water. So it's specific to a compound and also the solvents that you're working with. So because the compounds have the same molar mass, that term can be eliminated. And then the K value is the solute mass in the top layer divided by the solute mass in the bottom layers. And what we try to do sometimes here is we try to have the volume of the top equal to the volume of the bottom. If so, then we can cancel this out, right? And the way that we would figure this out if it was ethers, we would just take off the top layer, right? Because the top would be your ether, and then we'd evaporate that and calculate what the mass is. And the mass in the bottom would be the total mass minus what the mass is up at the top. Anyway, you can calculate your equilibrium constants or your distribution coefficients using that. So practically speaking, that number can be used to calculate the amount of solute in a particular layer. So you can use this quantitatively in OChem to demonstrate the need for multiple extractions. All right, so let's pretend, I know we can't do this experiment online, but let's pretend that we're doing it. So this is our experiment that we're going to kind of go through a dry run together right now. So what you're going to get is an unknown. Okay, so I'm going to give you guys basically a little conical vial, an online conical vial with an unknown, right? And the choices are going to be fluorinone, fluorine, 12,4,5 tetrachlorobenzene or triphenylmethanol. The important thing to point out is that all of these are nonpolar and will dissolve in nonpolar solvents. Now, in addition to that, we're going to, so down here you have your unknown. In addition to that, we're going to go over and we're going to scoop in an impurity. It could be an acid and or a base. The impurities are benzoic acid or ethyl 4-aminobenzoate. So what I'm going to do is I'm just going to use red there from one of them and then blue for the other. Mix them up a little bit here too. So they're all mixed up. Okay. So we're going to learn on the next page here, we're going to walk through and do something called a separation scheme together. We're going to show how we can purify our unknown, one of these four compounds, from the acid or the base impurity. Now we've already kind of talked about this a little bit. And we're going to take advantage when we do the separation of something that I like to call the solubility switch. So the solubility switch, you look for an acid or a base, and then you utilize acid-base reactions to change its solubility. So let's just take a look at this compound. This is ethyl 4-aminobenzoate. Okay, so if we take this thing and just look at it by itself, right? So if we had this thing, for example, inside of a test tube, right? You got your liquid in here. This is in ether. The question is it going to dissolve in ether? Well, ether is nonpolar. And we said before, we decided that this is also nonpolar. So this is dissolved in ether. Okay. Now, if we want to get this to crash out of solution, what we can do is we can recognize that that nitrogen is basic, and here we're going to add H3O+. Okay, so that means we're adding HCl-AQ here. All right. Now, when we do that, that nitrogen becomes protonated. So we form an ion. And because you have an ion, it's very polar. Ions make things very polar. So now this is soluble in H2O. Okay? So if you were to add that, what would happen is it would get protonated. Right, you'd have your two layers here. This is your ether layer. But now this compound, can't draw it in here, but this compound now is going to be in your aqueous layer. Okay, so it becomes soluble. Let's just make a note here. Soluble in H2O or AQ layers. Okay. Now, if we want to look at acid compounds, here's benzoic acid. So this is going to be soluble in ether. And then if you add a hydroxide, then that H gets taken away, and this becomes soluble in water. Okay? And of course, here the nonpolar solutes are right, here's naphthalene, but the example up above was right, fluorine, fluorinone, 12,4,5 tetrachlorobenzene or triphenylmethanol.